In this video we're going to talk about rotational motion. And here's a situation in which we have an object on a circle at position A at time t equals 0 and position B at time t equals f. And we want to come to grips with how to describe this motion just like we did with linear motion. Everything that happens linearly should have a rotational pairing. So first of all, we want to define angles. So if we say the angle is relative to the positive x-axis, then I can call that theta. And since it's at time t equals 0, I'll call it theta 0. Likewise, here I can call this theta f. And so I can think of rotating around in a circle by changing angle. So in the linear motion, we use x and y as our distance, and the units are meters. And in angular, we're going to use angles, theta, and we're going to measure angles in radians. So in this situation, what I want to emphasize is that everything we did in linear has a corresponding activity in angular. So for instance, velocity here equals delta x over delta t. Well, angular velocity, which is a Greek w, equals the delta theta over delta t. So really, rotational motion is one-dimensional motion. Typically, counterclockwise is positive and clockwise is negative. I can also talk about angular acceleration. So in acceleration, average acceleration is delta v over delta t. And in rotational motion, the rotational acceleration is delta w over delta t. Okay. Units wise, this is radians per second. So therefore, acceleration is radians per second squared. So in situations of linear motion, we have two kinds of problems. We have constant velocity. And in that situation, we really only have the one equation, v equals delta x over delta t. We also have constant acceleration problems in which we have three equations. Sorry. Each of these has a corresponding angular rotational equation. So we'll just do a translation here. My angular velocity equals my initial angular velocity plus the angular acceleration times t. My position theta equals my initial position theta plus the initial angular velocity times t plus 1/2 alpha t squared. And lastly, my angular velocity squared equals my initial angular velocity squared plus 2 alpha delta theta. Okay, so everything you know about linear motion, you now know about rotational motion. And that really makes it easy. Let's do a review of radians. If I have a circle and I have an initial point here and I take this arc length here called S, so that's the arc length, that's the distance along the circumference of the circle. If that moves from here to here, it makes an angle theta like that. Now, the definition of a radian is if the arc length equals the radius, then the angle equals 1 radian. That's about 57 degrees, and you'll want to remember that 2 pi radians equal 360 degrees. Okay. So this makes working with rotational motion fairly simple. So let's do a quick problem. Let's find my angular velocity if I'm going from an initial angle of 2.1 radians to a final angle of 6.8 radians, and it takes me 3.2 seconds. Well, I would just get the average. This is again average rotational velocity would just be the change in position, angular position, divided by the change in time, which would equal 6.8 minus 2.1 rads divided by 3.2 seconds. Okay. So that would be an easy thing to find. And what that would represent is a situation where I'm going from here to here in 3.2 seconds, something like that. So hopefully that makes linear and angular situations look a little simpler.